So that was two definitions of state, agent state and environment state. Now here's a more mathematical definition of state, which we call the information state, or sometimes called the Markov state. And the Markov state, or the information state, basically is an information theoretic concept. It tells us when we've built a state representation that contains all useful information from the history. So what we're going to do is we're going to define something. We're going to define a Markov property. So this is the Markov property. It's probably familiar to those of you who've studied anything to do with Markov chains or anything like that. It's the same idea. And the Markov property basically says that the probability of the next state, conditioned on the state you're in, is the same as the probability of the next state if you showed all of the previous states to this system. In other words, you can throw away all of the previous states and just retain your current state, and you would get the same characterization of the future. So let's just try and understand what that really means. So I like to think of it this way, that what this is really saying is that the future, what's going to happen in the future, if you have the Markov property, then the future is independent of the past given the present. In other words, that you only need to store this st here. If you've got this state representation S and it's Markov, you can throw away the whole rest of the history. You don't need it because that history doesn't give you any more information about what will happen in the future than the state that you have. That's what the Markov property means. It means you can throw away everything that came before, just keep your state, and you're good because you haven't given up anything. That state still characterizes everything about the future, all future observations, actions, rewards. The distribution over those events is the same conditioned on your state as it is conditioned on the whole history. So you can just give up this, work with something much more compact, and everything will be fine. So that's the definition of a Markov state. So we can throw away the history now. And another way to say the same thing is that the state is a sufficient statistic of the future. So this state here fully characterizes the distribution over future actions, observations, and rewards. So once we have this state, we can say everything that there is to say about that distribution. Yeah, question?
I think you said at the beginning, though, that the reward comes at many time steps after the action, the observation, and the action.
Yes.
So, I mean, how does that reconcile with the fact that you're throwing everything away except the previous time step?
That's fine. So what all we're saying here is that the way that this environment is going to evolve going into the future, that everything we can say about the future, the distribution of events that might happen to us, conditioned on this state is the same as if we conditioned on the full history. So we still have to figure out how to take the right actions. We still have to figure out what the optimal behavior will be. All this tells us is that if we make decisions based on S, those decisions can still be optimal because we haven't thrown away any information. We haven't talked yet about how to make decisions based on S rather than H.
Yeah. In your example of a helicopter, for instance, because clearly where it goes next depends on where it was before.
Okay, so the question was, how does this fit in with the helicopter example? So for the helicopter example, a Markov state for the helicopter would be the current position, velocity, angular velocity, angular position of the helicopter would be roughly a Markov state for the helicopter. Once you know all of those things, and maybe you need to know the wind direction and things like that as well, but if you know all of those things, it doesn't matter what the position of the helicopter was 10 minutes ago. That doesn't make any difference to where the helicopter will be at the next moment. All that matters is where it is now, and the wind direction, and that will fully determine what will happen to the helicopter at the next moment. You don't need to remember this detailed history of its previous trajectory, because it's irrelevant. In contrast, let's say you took an imperfect state representation that's non-Markov, like you just had the position but not the velocity. Okay? Now, where the helicopter is does not fully determine where it will come next, because you don't know how fast it's moving, and so you have to look back in time to figure out actually what its velocity is and what its momentum will be, all these kind of things. Okay, so that's the information state or the Markov state.
Can I just ask one question? On this, we're saying that the state, if we know the state, then we know everything there is to know about future states.
Yes.
But that itself is not necessarily very helpful, because the state might be nothing to do with the reward.
Okay, so this history, don't forget that the history includes all rewards. So to say that it's a sufficient statistic of the future means that it's a sufficient statistic of all future rewards. So that, by definition, means that a Markov state contains enough information to characterize all future rewards. Okay, So I want to give two just brief examples before we move on. So one thing to note is that the environment state, if only we had access to the environment state, that would be great, because the environment state is Markov. By definition, the environment state fully characterizes what will happen next in the environment, because that's what the environment is using to pick its next, the next observation it's going to emit is and the reward. So sort of by definition, the environment state is Markov. Also by definition, if we keep the entire history of everything, that is also a Markov state. It's just not a very useful one. But if we retain everything and make our decisions based on the entire history contains as much information as the entire history. It's sort of tautological, so therefore it's Markov. So these are two examples where we can, to show that there's always a Markov state. It's always possible to come up with some Markov state. The only question is, in practice, how do we find a useful representation? Okay, so let's